Hi, my name is Riley Heath, and I am an environmental science major and a first year at UNC. I want to add chemistry and double major because I am very interested in the nexus between environmental science and analytical chemistry. So I took Chem 101 last semester and I absolutely loved it. And I'm in Chem 102 this semester and also absolutely love it. I have just found it so interesting, and the material to me is just so exciting because college is stressful and life is stressful. I was having a bit of an anxiety attack one night, and so I sat down and I pulled up the chemistry textbook on my laptop and I just read it, and it was absolute zen. Like, it was brilliant and so calming. And that was when I was like, okay, maybe this is a sign that this is a good field for me. So anyway, I would absolutely love to be a chemistry LA because for me to love it this much, I'm like, okay, obviously I want to share this joy. And so I think that would be a great outlet for me to do so. And also, I feel like I do understand the curriculum, but I also have a very deep understanding of the concepts, not just the base level curriculum. And so I feel like I might be able to provide a variety of explanations to students that might have questions or might have heard explanations before but haven't found one that really resonates with them yet, that clicks in their brain. And so I feel like because I understand it, I might be able to also help other people understand it in a way that makes the most sense to them. So yes, now I'm going to take you through a practice problem. Sorry, that's an ad. Okay. So this is from the first exam this semester. And we are looking at creating the energy required for the formation of magnesium oxide. So we first are going to look at the three reactions that it gives us, and the enthalpies of change associated with each of the three. And then let's just look back and see how that connects to our big overarching reaction. So our two reactants are magnesium and oxygen, and we're looking at forming magnesium oxide. So let's look for where these are reactants. So we see magnesium is present in solid form here, and oxygen is present in solid form here. So because these are each the reactants in their respective reactions, and they are in the quantities described that match the reaction it gives us, therefore meaning like the stoichiometry of the reactions is the same, we don't have to do any like dimensional analysis or conversions. That is 1 magnesium and 1/2 oxygen. These reactions will just proceed as normal. And so that means that their enthalpy of the enthalpy of the reaction is going to be exactly what's written here, because it's proceeding left to right. And we can also see that, for example, the hydrogen that's listed here then plays into the hydrogen associated with the oxygen. We can see how the reactions are connected. However, we're left with this reaction in the middle, and we formed water and magnesium chloride and hydrogen, but we have not formed hydrogen gas, that is, but we have not formed magnesium oxide yet. So if we look, we can see that it's actually a reactant in this middle reaction, and therefore the reaction will proceed in reverse, which means that this value will become positive because it's not releasing this much heat. If it's running in reverse, it's actually requiring this much heat. So that just means that we're going to add the three written values together. Let me get out my calculator. So we're going to make this middle one positive, considering it's running in reverse. And that means that if you add negative 462.9 plus 147.5 minus 285.8, you get negative 601.2. And you just want to